Hello everyone, my name's Sina BaniasadAzad, and in this presentation I will talk about LPCNet, lane detection by lane points correction network in challenging environments based on deep learning. This paper is in the field of lane detection by deep learning, and the keywords related to the paper are lane detection, deep learning, lane segmentation, and structured road autonomous vehicles. So, why lane detection? As the number of self-driving cars increases, the advanced driving assistance system develop in parallel. To a large extent, the frequent occurrence of traffic accidents is caused by subjective reasons related to the driver, such as drunk, tired, and incorrect driving operations. Smart cars can eliminate this human factor to a certain extent and intelligently help humans perform driving tasks based on real-time traffic information, thereby indicating the scientists in improving the safety of automobile driving and liberating human beings from tedious driving environments. One aspect of automation that we share with this autonomous system is road lane detection. Lane detection is critical in recognition and ensuring safe driving practice. An onboard system with capability can alert the driver in the event of unsafe lane change. Lane detection is also instrumental in understanding road layout and surrounding scene geometry for proper road planning. Until the deep learning method was not introduced, lane detection was done by geometric model that relied on highly specialized and handmade features. These feature selection include color-based features, edge, and energy minimization algorithms, often use algorithm of traditional methods, generally used for steps, image preprocessing, feature extraction, model fetching, and post-processing. Existing methods have certain limitations. For example, they have acceptable accuracy in suitable weather conditions, but they haven't been tested in challenging weather conditions such as foggy. On the other hand, the high accuracy of existing models increases the parameters and computing power of the system. Self-driving cars are limited in processing power, and many models with reasonable accuracy are not practical. Also, in desert roads, where the texture of the road is difficult to specify from inside the area, we reach acceptable accuracy. So we know other articles in desert areas have not reached such accuracy. This model is also accurate in the absence of road markings. The situation where the road texture is weak and does not have a line, additional points unrelated to the road line are generated. Also, with the production of additional points, the speed and accuracy of the model will decrease, and it won't be easy to decide to control the self-driving car. In this case, human life is at stake, and the model must make a quick decision, but the extra point generated are a problem that our proposed model solves. CNN proposed an algorithm using deep learning and new ST architecture. The ST architecture uses several frames to detect line in the current frame. The architecture solves the segmentation problem using end-to-end supervised learning. Using two neural networks, CNN and RNN, an algorithm for lane detection has been presented in three references. In this method, the CNN network detects geometric features such as the position and direction of the desired target, and the RNN network has the task of structured visual recognition. The core lane NAS algorithm using three modules, a feature fusion search, an elastic backbone search, and an adaptive point blending has presented a method to improve the detection of curved lines. Also, a dataset containing 150 images of urban areas and highways has been introduced. The RCN algorithm performed the segmentation of objects using CNN and proposed a scalable method. With the faster RCN algorithm, a proposed region network has been introduced and has achieved significant speed and accuracy. In the YOLO algorithm, object recognition is presented as a regression problem. Our proposed network consists of two stages, lane detection and lane modification. In the lane detection stage, we use a simple model that is effective for real time, and in the lane correction stage, we correct the predicted point using the Ramsek algorithm. Depending on weather conditions, road texture, and color, lane detection algorithm may generate additional points or even detect lanes that are not the road lane. We remove the extremes with the predicted point and lane correction approach. Figure 6 shows the general methodology of this research. The stack-Hourglass network has been used for lane detection to detect critical points. In the proposed network, the loss functions are adapted from the YOLO network to reduce the prediction error. The exact point of the lanes are predicted by the offset and confidence branch. Also, the embedding embedding branch produce the properties of each projected point. The ransack algorithm considers the points with the highest probability as lanes and removes the other points. If an extra lane generated, ransack algorithm detects it and removes it. Figure 7 shows the framework of the proposed network. The input image enters the resizing network and then the output of the resizing network is entered into the prediction network. The result of the prediction network has specified the lane and vertical point style due to challenging weather conditions or road texture. It produces additional points that do not belong to the road lane and should be removed. Therefore, the output of the prediction network enters the point correction network. In this network, the extra points are removed using the ransack algorithm. The confidence output branch detects the value of the K points in each section. If there is a K points to each section, the value of the output branch is close to 1. And if there is no K point in each section, this value is close to 0. The offset branch checks the possibility of the critical points of the output cells with a value between 0 and 1. For example, if the cell has 16 pixels and the value calculated by the offset output branch is 0.25, the critical point is 4 pixels outside the desired cell. The future loss function from SGPN, similar to group proposal network, is a segmentation method for 30 points, and it divides the points with the same and different features. The resizing network is shown in Figure 9. The size of the input RGB image is 512 in 256. This image is resized to the network and compressed to 64 in 32 by convolutional layers. The output of this network is given to the prediction network. Also, if the size of the extracted frame is different from the resized network input, a preprocessing step is required. The output of the resizing network is transferred to the prediction part to extract K points. The point detection network consists of 4 modules, encoder, decoder, and 3 output branches. This network has the ability to move some information to deeper layers on an scale. And this feature is used for downsampling in convolutional layers. After detecting the critical point by Hourglass and convolutional layers, the results are entered into the ransack algorithm. In the subsystem, the points with the highest probability are selected and other points are removed. Suppose a lane has 10 points and we chose the error limit of 5%. This algorithm removes the points more than 5% away from the ground truth data. The error limit can be variable according to the environmental conditions and the purpose of the system. Another figure shows the lane detection of the recognized point by the ransack algorithm. Our dataset is specially prepared. In foggy conditions, the camera angle and light conditions are not suitable. Also, the quality of the image for detecting the edge of the road is low. In desert environments, conditions such as low contrast between the color of the road and its surroundings and the texture of the road make it challenging for lane detection. There is no suitable standard for understanding the line by the neural network on the road without line drawing. We use 2,838 images for training and 1,213 images for testing. The proposed model consists of 2 parts, detection of points and correction of detected points. To calculate the complexity of the proposed algorithm, we calculate the number of parameters in these 2 sections. The number of parameters of point detection algorithm is estimated to 4.06 million, and after improving the result, only 0.51 million parameters are to add to the calculation. Equation 1 shows the computational complexity added to the system by the detected points and correction algorithm. O is the number of repetitions required to correct the points. PS is the probability of success in correcting points. PS is the percentage of out-of-line points that need to be corrected. And finally, S is the number of points the algorithm considers as main points. In table 4, the number of formats of the model is compared with other valid models. The reasonable computational complexity of our model is visible. Foggy conditions are a scientific challenge for line detection because, in addition to reducing the field of view of the camera, it also reduces the quality of the image. The proposed algorithm has promising results for foggy conditions. In desert conditions, the color difference of the road is so small that image processing, such as color enhancement, have little effect on improving the. In addition, the texture of the road is raw, and the width of the road is not the same in all parts. In the absence of road markings, there is no sign for the autonomous vehicle to perceive the road. The proposed algorithm detects the line points by knowing the difference between the road and the surrounding environment. Also, the proposed system has been tested in unstructured environments. Its results are competitive with the model tested in structured environments and show the value of our work. Sensor integration is usually used in challenging situations to increase accuracy, but the proposed model with excellent accuracy reduces the need for other sensors of the self-driving car, avoids further complexity, and helps to implement a practical and robust system. Figure 13 shows the implementation result in challenging conditions. The result of the proposed algorithm were shown in foggy, desert, and online environments. We achieve excellent accuracy in unstructured environments without increasing computational complexity. With the progress of deep learning, there are still many problems with lane detection in unstructured environments, such as desert, night, foggy weather, online road. These problems make the general application of self-driving cars as a challenge, and with this challenge, they cannot be used in all situations. In this study, by proposing the LPCNet algorithm, we achieved a suitable accuracy in challenging and unstructured environments. Also, the computational complexity of the network is ideal for real application and is less complicated than many valid methods. So in future work, we plan to use previous frames to predict points and detect lines in the current frame. Learning earlier frames makes it possible to overcome challenge situations better. The performance of lane detection, driving area, and object segmentation tasks can also be considered complementary tasks. Also, in addition to lane detection, the task of object detection or driving area detection can be added to the algorithm, and a multitask model can be proposed. Integrating LiDAR sensors with cameras and using depth estimation or other future works. Adding a pre-processing network to remove image noise or increase color difference can be another task. Thank you for your attention.